Professor Dravid conceived of this Tech Talk idea several years ago, primarily as a chance for our users to connect with staff in a relatively less formal, non-lab setting. So we used to have coffee over in Cook, and we're hoping to be able to have coffee and treats over in the AB wing as soon as we get through this pesky pandemic thing. So in the meantime, Katie, Tears, and Paul, and several of the other staff members worked very hard to come up with a virtual version of this. So I'll turn it over to them in a minute, but I just wanted to say, this is really a chance for our staff to kind of show off anything new, bright and shiny, maybe. And for the users to really, interact one-on-one in a less formal setting. So please don't take this as, a formal talk. This should be very comfortable, collegial. Imagine that we provided you with coffee and donuts or something that you like to eat. And then after the presentation, we'd like for you to have questions. So if you want to put the questions in the chat as the talk goes on, that's great. If you want to wait and interact with your voice after the talk is done, that's very good as well. So with that, I'm gonna
shut my mic. Chad, if I just do a 10-second to just again thank everybody, and particularly our team, to pull this together. There's a lot of effort that goes into arranging this. I really applaud and appreciate all the effort. And in terms of role responsibility, you as users and who are attending this webinar, look at our capabilities. This particular one is actually a loaner system, and I suspect Paul and Tirza will elaborate a bit further. But we do this in order to get some feedback, get our staff to use different types of instruments. And this really makes sense for us as a user facility. Then we work hard to get the resources to buy this instrument. So please review it in this context, that do we need this capability for your research, for your collaborators' research, and how we can help improve our operation at Nuance. So with that, again, I welcome everybody, and Paul and Tirza, please take away. You've got a great program you put together.
Well, thanks, Chen and Vinayag, for the introductory words. So currently our participants are relatively stagnant, so I'm guessing we'll get started. So for those who not know me yet, my name is Paul Smeets. I'm a facility manager at FIB TEM in the EPIC facility. And together with my colleague Tirza Abbott from the SEM facility, very excited today to host today's Tech Talk. And so, although we currently live in somewhat darker times, we hope to get the research community together with, amongst others, this Tech Talk and demonstrate that the future indeed will be bright. Now you see that I underlined FIB, so that not only stands for Future is Bright, but also for Focused Ion Beam. So with that, we're going to talk about this new tool that you see over here. That is the Joule JIB 4700F multi-beam system. This is how it's advertised at Joule. And this is how it currently stands in the Technological Institute on the ground floor in room number AG98. And so the multi-beam system basically has two types of beams. It has an electron beam and an ion beam. And with that, you can do some very cool things. So I'll show you in detail some more capabilities of this 4700. But before I do that, I'd like to first talk to you a bit about a small amount of theory. So what actually is a dual beam FIB SEM? So we're all familiar with the standard SEM format where we have an electron gun where a beam of electrons is emitted onto a sample, and that sample is attached on a stage that can be tilted, rotated, translated. And this interaction will lead to typically secondary electrons that are then scattered towards a detector. And from there, this detector will display it on a monitor as an image. Now, for an FIB SEM principle, so we can rotate the stage typically about 52 to 55 degrees to basically make this sample coincident with a second beam. So in this case, an ion beam. So that's hence the term focused ion beam, which can shoot high energetic ions onto a sample and sputter away atoms in your sample, so sputter particles. And then the SEM can, for example, serve as imaging a cross-section of your sample. So you can selectively remove specific atoms at this selected area of interest. Now, the 4700 has a myriad of capabilities, and most of those that I'll discuss today are with regard to sample preparation. So you can create TEM, small, tiny, transparent samples. You can even create atom probe nanotips, cross sections that I already mentioned. So I like to think of this tool for sample preparation kind of as a Swiss Army knife. So it has multiple functions, and you can create all kind of shapes and structures on the micro to nanoscale even. So specifically regarding sample preparation, the SEM standard is used for imaging the surface or cross section, as I mentioned, but the FIB can also be used not only for imaging or sputtering, as I mentioned in my previous slide, but also, for example, to deposit material on a region of interest that, for example, needs to be protected. This is typically done using a gas injection system. So here you can see this gas injection system, which then typically emits organometallic material, which has a volatile component and a non-volatile component. So the volatile component is typically organic that gets removed, but you end up with deposition of, for example, different types of metals. And in the 4700, we have platinum currently available, but we also have carbon that can be deposited. Another function that we have is we have a micromanipulator present, which you can see in this diagram over here, which is basically a very sharp tungsten needle that can be inserted to remove specific microscopic or nanoscopic regions of a sample and then isolate onto another substrate. So that's one capability, the sample preparation, so manual sample preparation. But this 4700 has also recently acquired new software where you can perform automated sample preparation with, not only for TEM, but also for other purposes. So I will also address this. And then my colleague Tirza will take over and talk about 3D tomography capabilities, or also, as people call this, slice and view, where you slice with the ion beam and view with the electron beam. She also will talk about electron backscatter diffraction and even 3D electron backscatter diffraction using a very fancy Oxford symmetry high-speed detector that we have. And lastly, she will talk about high-speed EDS that we can also acquire with a high-speed silicon drift detector. So let's start with sample preparation, so conventional TEM samples. So as I mentioned before, we can insert a gas injection system, and we can use the electron gun to deposit a little bit of platinum on a region of interest before tilting the stage 53 degrees in this case towards the ion gun, and then deposit some more platinum. As here you can see the FIB image view, and here is the SEM image view. Now, a next step would be to mill trenches, so typically using higher energy ions. In this case, we have gallium ions that remove selectively removes material near our sample of interest. And in a next step, we tilt to 0 degrees so that we can reach with the FIB underneath the sample, so make what people call a J cut. So this is the shape of a J. Some people call it a U cut, but I see more of a J in it, to be honest. And Then in the subsequent step, we can bring in our micromanipulator, so the tungsten needle, we can weld it on, cut the other side free, and lift out our region of interest. And the next step, we can mount it on, for example, what's typically done for TEM sample prep on to a copper half grid, which has these different type of posts. And we can attach it to a side of one of those posts, use, again, platinum deposition to attach it, mill the OmniProbe loose, and then we can start thinning our sample, so typically at 53 degrees. So when we're coincident with the ion beam, we can selectively mill a specific region, then use lower energy ion milling to to remove material to a smaller degree. So lower energy basically removes less material. And we can end up with a small sample where we have a electron transparent window. So this is the electron transparent window. Typically that indicates, if you see this, that the sample is below 70 nanometers in thickness. Then if you look at the 0 degree tilt, then we can measure that in this case, we have a 36 nanometer thick lamella that we've prepared using the focused ion beam. And this is ideal for transferring it to the TEM or STEM in the case of inorganic samples to watch atomic columns. Or you can do spectroscopy like EELS or EDS in TEM or STEM on these type of samples. The second sample prep manual that I would like to talk about is atom probe tomography. So similar to our TEM sample prep, we deposit typically a large bar of platinum using the electron beam. Then we do the same thing for the ion beam, deposit some more platinum. We mill our trenches in a specific way. So we're tilting our stage at 22 degrees. So the ion beam basically comes in from this angle. So if you would look at the side of this bar, your ion beam would come in from one side. So you cut it here. Then you rotate the stage 180 degrees and you again mill at 22 degrees. So from the other side here. So this is basically a triangular bar that you're milling. Then you bring in your micromanipulator again, weld it on, cut the other side loose, and lift out this triangular bar. And for atom probes sample preparation, typically it's transferred. This bar will be cut into chunks on a silicon array with silicon posts. So this is the schematic over here at 0 degree tilt. Here we're approaching our bar to one of those silicon posts. Then we weld it on using the platinum that we have here again. We cut this chunk loose. Then we also put some platinum on the other side to make sure that the chunk is stable. And then we're going to use a circular milling technique to subsequently increase the magnification with coincidence to the ion beam, so at 53 degrees tilt. And so we'll have an annular pattern like so, where the inner circle is preserved, but the outer circle is subsequently milled. So we end up with a with a nanotip that typically looks like this. After some final cleaning, we can end up with a tip that looks like this. In this case, it should be a little bit below 50 nanometer wide nanotips that you can prepare. And these tips you can then transfer to the atom probe that's available in NuCAPT, and then you can in 3D determine your composition of this nanotip at the atomic scale. So here it's visible that this sample preparation is typically an initial but also crucial step to materials characterization that you can perform with the FIB. So I talked that we have an OmniProbe present, but the cool thing about this system is that it can acquire and deposit these tungsten tips in situ, so in the vacuum of the chamber automatically. So if we look at the sample holder, the OmniProbe holder, we basically have our sample. In this case, it's a silicon wafer. We have our TEM grids where we can transfer tiny lamella onto the posts. And we have 2 tips that we can put on this holder as well. So this is a zoom in of this part where you can see the OmniProbe. Here is the tungsten needle. And so the acquisition can be performed automatically. So as you can see here, this takes about 5 minutes or so. So this is the SEM image where you grip and you position the a gripper in the ion beam, and then it acquires it automatically within the vacuum. So no need to pump down the chamber, change out the OmniProbe, and pump down the chamber again, like we have to do in our Helios. And so it also automatically deposits the tips. So again, this is a matter of I would say it's about 1 to 2 minutes that it takes, and it automatically deposits in just a few steps. So I also said I would address automated sample preparation. So we have this software called Stampling, where you can automatically perform TEM lamella preparation. So typically what it can do, so this is the interface of the software where it can deposit a marker. So typically the marker is consisting of platinum with some type of holes. So that uses the software as an alignment marker to do this whole TEM sample prep that I showed you automatically. So you have a lot of options. You can change the sizes of your lamella, the thickness, the height, the width, you name it. You can change that in the software. So I'm going to show you a video of the subsequent steps. So these are all automated images that are acquired with the software as well. So you can start your experiment, walk away, and then let the instrument do this job for you. So here we start with that marker. So in the next step, we deposit our platinum bar. Then we mill one trench, we mill the other. We clean up both sides using a lower energy beam. Then we're tilting towards 0 degrees. We do a cut underneath, a cut to the side, another cut on the side, and leave it hanging on a very tiny amount of material, and clean it up. So this is the pre-prep part that now only takes, takes about 25 to 30 minutes. So significantly faster if you would do everything manually. So here are the still images that shows this process as well. And so not only TEM sample prep just can be acquired using this software, but you can also make cross sections, for example, again with the same marker, or pre-processing for 3D observation, which Terza will address a little bit further down. And also you can create in one automated process several of these lamella prep and on different materials. For example, on silicon here, this is silicon, but this is on copper, and you can see that there's also different heights. So you can all pre-program this and let it run through several of these processes as well. And with that, I'll turn it over to Terza.
Thank you, Paul. So I'm going to finish up by going over some of the other techniques and tools that you can use on this particular instrument. Paul already mentioned this. You could see that the stempling software does offer a method for actually automatically milling away the sides of an area of interest so that you can perform slice and view imaging. Basically, what this does is the software for the FIB will allow you to designate thickness of certain, or a series of slices that you can slice away from your block and then capture an SEM image after each slice. So there's a little animation of, probably not the best sample to show this, but it does show that it's slicing away with the FIB and then it's capturing an image with the SEM. And from that stack of images, you can recreate a 3D object. So there's just an example here of a solid oxide fuel cell showing the volume that the nickel and cerium, gadolinium oxide and pore spaces take up. This system is really nice because if you do use the stempling software, it does provide you with that marker. And that marker is very useful to help correct for any drifting that you experience while performing this analysis. That is an issue that is commonly seen in FIB and our other FIBs. So if you're trying to do a really long experiment doing slice and view, which can take several hours or even a day to get a full data set, you want to avoid the drifting. Otherwise, it will completely destroy your data set. So Paul, if you could go to the next slide. This microscope also has the new Oxford Symmetry EBSD detector. So if you're not familiar with EBSD, it stands for electron backscatter diffraction. So this detector can collect 3,000 patterns per second, which will mean a little bit more to you in a second when I explain. It can perform large area mapping and can capture really high resolution EBSD maps very quickly, almost at the same speed as you can capture an EDS or a high resolution, high quality EDS map. And this is very useful on an instrument like a focused ion beam, because then you can perform slice and view and do 3D EBSD, and I'll explain a little bit more later. So Paul, if you could go to the next slide. So if you're unfamiliar with EBSD, I'm going to explain a little bit about how it works. So as the electrons interact with your highly tilted sample, the tilt helps to increase the number of diffracted electrons. Paul, can you click? The electrons are diffracted from the sample along the crystal lattice, or the planes in the crystal lattice, and hit our EBSD detector. So as it diffracts and hits the detector, it creates, or as it diffracts, it creates diffraction cones, which are at such a low angle that when these cones hit the detector, they appear as lines. You can see it kind of looks like there's 3 lines there. The middle line is the one we're interested in, and there are usually 2 darker lines on the top and the bottom from the diffraction cones. And Paul, if you could click again, those lines are called Kikuchi lines and form this Kikuchi pattern. And so the symmetry of the crystal lattice is reflected in these patterns, but how do you analyze this? So Paul, if you could go to the next slide. So unfortunately, computers are not smart enough to look at this picture of this Kikuchi pattern and determine what the crystallography of your sample is. So it actually transforms it into Huff space, or in a Huff transform, which converts all of those lines into points. And those points are referred to those specific lines in the sample. And those points are a lot easier, can be more accurately ID'd than those lines. And they correspond to the zone axes in the crystals. So as the beam is scanning across your sample, as the Kikuchi pattern changes, so does the crystal, or the phase, or the orientation of that crystal, as you can see in this animation here. To determine what the phases and the orientation is, we compare the results from the Huff transform and the Kikuchi bands to a database. So EBSD, you need to have some prior knowledge of the crystal, or the crystal systems in your sample. The EBSD detector cannot identify unknowns. So the Oxford software has 3 different databases that you can pull information from, but if you know the crystal parameters or the lattice parameters of the crystals you're trying to identify, you can also add that with the Oxford software. So this is the typical data set that you'll see from your EBSD data. You can see the Euler angle map, which is on the bottom in the middle. And that's a common way to describe the sample orientation, but small color, or the color variations are often extreme, and so they don't show slight variations in orientation very well. So you can display an inverse pole figure. So the inverse pole figure assigns a color for each corner, or each zone axis. And you can display a map relative to whichever reference direction if you know the reference direction of your sample. So whether it's relative to the rolling or transverse or normal direction. And you also get a map showing band contrast that shows the quality of the Kikuchi pattern. You can see that in your phase color map, it's all the same phase. This is a single phase sample. And you see dark lines between the grain boundaries. Now you wouldn't see this in EDS either because the composition is the same across the board. But when you move from one grain to the next, the Kikuchi patterns can overlap, making it harder for the software to index those. So with this band contrast map, you can actually determine different grains in your sample very easily. So Paul, if you could go to the next slide. EBSD does have some limitations. You can't analyze rough surfaces. This interferes with the diffracted electrons, making it to the detector. So you have to have a really fine final polishing step, either ion milling, electropolishing, and you cannot obviously analyze amorphous or distorted samples because they don't have crystal structures, which is why this is an analysis that's typically used for metals, alloys, and geological materials. You can only analyze grains that are bigger than about 25 nanometers. Because you have such a highly tilted sample to increase the number of diffracted electrons, you lose spatial resolution. So if you can see in that figure, that light green area that's interacting with the surface of the sample is quite large. One of the ways to get around this is to use what's called TKD, or transmitted Kikuchi diffraction. And it's really convenient because you can prepare your TKD samples with the focused ion beam using the TEM sample prep procedures that Paul just went over. So you make a very thin sample, and the beam interacts and transmits, and the Kikuchi pattern or the diffracted electrons are actually projected onto the phosphor screen. So you can do this. It's kind of like a one-stop shop with this instrument because you can do it all on this one instrument. So let's go to the next slide. And another nice feature is, if some of you have used EBSD before on one of our other microscopes in the lab, we have one on the Quanta 650F, you know that post-processing the data can be kind of a hassle because each kind of post-processing feature analysis you want to do requires a different software package. But Oxford has combined that into one called Oxford Crystal. So you can do all of your cleaning of indexed pixels or misorientation analysis, grain, calculating grain size. You can create pole figures. You can do it all in this one software interface. So, and then finally, because we have this EBSD detector that can collect patterns incredibly quickly, and it's in a focused ion beam instrument, we can actually perform 3D EBSD. So the software is also integrated into the, or the JOL software is integrated into the Oxford software. So it will, you can use the slice and view setting in the JOL software to cut a slice, and then the Oxford system will take over and collect an EBSD map. So you can then create your 3D object that way. All right, so next slide. So this also has a 100 millimeter square silicon drift EDS detector. You can also perform 3D EDS mapping as well. And this particular Aztec license has all of the bells and whistles. Sorry, they just started cleaning my windows. So this is a little video showing another feature that's new to the lab. We also have on the JOL 7900. It's Aztec Live. And so what this allows you to do is create a compositional map while you're scanning or moving the stage underneath the beam. And this is really nice for the focused ion beam because if you have a sample that you need to find a specific area of interest to create a TEM or atom probe sample, you can use the EDS system to find it and then perform your sample preparation. Okay, next slide, please. So just to kind of wrap up, the JIB 4700F multi-beam system has a lot of new capabilities to offer in the lab. So it does have a high performance SEM with really high resolution. It has both an in-lens and lower SE detector, as well as a dedicated backscattered electron detector, which is another new feature on this particular FIB for us. It has a hybrid electrostatic electromagnetic lens, so you can image magnetic samples. And it has beam deceleration, so you can apply a negative bias to the stage to reduce the interaction volume of the beam with your sample. It also, on the FIB side, has a much higher probe current and can mill very quickly. And it has just a bunch of bells and whistles. It is truly a Swiss Army knife. You can do 3D slice and view imaging. It has the silicon drift detector, which you can also do 3D EBS with, the new CMOS EBSD detector for 3D EBSD, and a fully automated sample preparation system. And of course, the OmniProbe, which is a newer version of the OmniProbe that than the other instrument, which we're going to go over in the next slide, which is more stable, we've found. So again, everything that's starred in red is kind of a new capability in the lab, but we do have another focused ion beam instrument in the lab that has additional capabilities, like the Wraith ion beam lithography system, or we have a Klein-Dieck nano manipulation system. It also does 3D slice and view, and it actually has a STEM detector, so you can do low kV STEM imaging with this, the SEM in that FIB as well. I don't know if Paul, you had anything to add, but otherwise, if you have if you want more information or have questions, you can contact me and Paul and Nathaniel Kabat. We are looking over the this particular instrument. And what was I going to say? I'm going to send out a survey after this to kind of get some information about your interest in the instrument. So Paul, I don't know if you have anything to add.